Good morning, everyone. Today we will have the talk by Imanol Unanue titled Advanced in Ranking Generated by Pseudo-Boolean Functions. So whenever you want, Imanol.
Thank you, Unai. Good morning, everyone. Thank you for coming. As Unai said, I will present our work titled Advances in Ranking Generated by Pseudo-Boolean Function, and this work is supervised by Maria Merino and Jose Antonio Lozano. So I divided this presentation in 4 parts. I will start with the background and the motivation of our study. Then second, I will present the Walsh decomposition, the Walsh transform, and I will calculate several Walsh coefficients or several binary-based combinatorial optimization problems. In the third part, I will consider the presented results in the Walsh decomposition to present a characterization of pseudo-Boolean function and several results related to it. And finally, I will present several experiments that we have run to understand and to try to understand a better comprehension of the rankings generated by the unconstrained binary quadratic problem and the number partitioning problem. So let's start from the beginning. So a brief reminder. We have the combinatorial optimization problem, which are the problems in which the goal is to maximize a function, which is denoted with f, and the solutions are taken from a discrete search space. When this space is the sequences of length n, binary sequences of length n, we can denote them as binary-based combinatorial optimization problem. And all the binary-based combinatorial optimization problems can be rewritten and redefined as pseudo-Boolean functions. So we have at the bottom of the slide simplification to understand how the function f works. Throughout this work, we will use the reverse notation. So as we can say, for example, for the solution x, we will read from left to right, starting from n up to 1. Okay. One consideration that we have taken into account for this work is that we will consider, instead of the specific definition of the rankings of the fitness function, we will rewrite it as rankings of the solution. So let me explain with a brief example. So we can observe, for example, the function f that we can calculate all the fitness function, and according to those fitness function values, we can order the solution. We can say which is the best solution, the second best solution, and so on. So we have an ordering of the solution. So we will denote a ranking of the solution defined by the fitness function f with the letter r, and we can also rewrite them as a matrix. It must be mentioned that in general there are infinite pseudo-Boolean functions which generate the same ranking of solution. For example, if we add or we remove a constant term, the ranking will keep the same. So this is very important because it simplifies the range of different scenarios that a problem can present. This is very useful, for example, for local-based algorithms and those algorithms that they do not consider the specific fitness function values. Moreover, we can also consider there is an association between all the injective fitness functions and the space of permutation of length 2 to the power of n. So the initial point of our study is an article very well known and very relevant in the literature called the non-free-lunch theorem for optimization, and it has several results, but one of the main results is the following one. It says any two algorithms designed to solve combinatorial optimization problems will perform on average equally well over all the combinatorial optimization problems. So this is very relevant because it says that it doesn't matter overall the algorithm, but it is very important to determine having a combinatorial optimization problem or having a combinatorial optimization problem means that which is the best or the most efficient algorithm to solve it. So this is the main research question. It is also known in the literature as the algorithm selection problem, and I have a brief schema to understand which are the main parts of this problem. So we have 3 parts in this problem, which are the first one at the top left of the corner, which is the combinatorial optimization problem, in which we want to extract the features and the characteristics of it. Then we have the second at the bottom, which is the bunch of algorithms to solve combinatorial optimization problem, which are studied theoretically. And finally, we have the final decision, which is how to evaluate the performance of those algorithms without evaluating with all of them. So these are the 3 key points of this scenario, and there are two main theoretical research lines. As I said, the algorithm theoretical research line, in which we study things like the convergent behavior, the population sizing, the computational cost, and so on. And then we have the second part, which is the combinatorial optimization problem or the combinatorial optimization problem instances, in which we want to extract the features to understand which are the easy or hard instances, if we can generate the fitness landscape or the number of local optimal solutions, and so on. So these are the two main theoretical research lines, and in this speech I will focus on the second one, on the latter one, and I will present the mathematical tool considered to this work is the Walsh decomposition. So this introduces us to the second part, which is the Walsh decomposition. The Walsh decomposition, it was a decomposition presented by Joseph Leonard Walsh in an article titled A Closed Set of Normal Orthogonal Functions, and it presents a complete set of normal orthogonal functions in which it works similar to the Fourier transform in the continuous function. A brief reminder, we have for the continuous function, the Fourier transform, what it makes is to consider the base of cosines and sines, and then according to them try to approximate that fitness function. So the Walsh transform has been applied in the literature, and several examples of those problems are the surrogate model for black box optimization to study the linkage discovery problem or to recover polynomial with a small degree monomials. Still, we think that Walsh transform, it gives us more information about it. So one of our main goals is to take into account the Walsh decomposition and the Walsh transform to try to understand better binary-based combinatorial optimization problems. Which are the main advantages of using that? Is that first of all, that we take no matter the definition or the specific particularities of the combinatorial optimization problem, and we take them to the Walsh function, which is, let us say, like an abstract word in which we can compare all of them. We can observe the equivalences, the relations about it, and we can also study the number of scenarios that each combinatorial optimization, each binary-based combinatorial optimization problem can generate. So throughout this work, I will mention two of them, which are the unconstrained binary quadratic problem and the number partitioning problem. So this is the formal definition of the Walsh decomposition. I will not read all the formulas, of course, but just to consider, it's an additive decomposition, and if we have a function defined over the binary sequences of length n, we require 2 to the power of n Walsh functions, and the Walsh functions are defined as a multiplication of +1 and -1. Each Walsh function is also denoted with binary variables, and we will use throughout this work the sub-indexes to understand which are the associated binary variables for each Walsh function. Okay. Overall, the Walsh decomposition of a pseudo-Boolean function is unique, and there are several ways to calculate it. However, one of the main drawbacks of this decomposition is that if we wanted to calculate the Walsh decomposition of a particular fitness function, we require to know all the fitness function values and to know the ordering. So that's our main drawback. However, we will see that there are several binary-based combinatorial optimization problems that they must follow a pattern, and because of that pattern, it's not required to calculate all of them because we in advance know some of those results. So the most mechanical way to calculate the Walsh decomposition is the Zildov's construction, which is a matrix multiplication. We have a matrix H, which is called the Hadamard matrix, and which is implicitly the information of the Walsh function, the +1s and -1s. And then we have the matrix of the fitness function values. Let's see a brief example. We have, for example, the following pseudo-Boolean function. So because it's of order 3, we calculate the Hadamard matrix of order 3, which is the H sub 3. And then we calculate also all the fitness function value, which is in the matrix F. So we can calculate, considering these two matrices, we can calculate the Walsh coefficients of it. Just a brief observation, we can, for example, see that the matrix F overall has some numbers of null values, and the Walsh coefficient has another number of null values, and they can be higher, equal, or low. So there is no overall relation direct according to the fitness function value. We have also a checking at the bottom. For example, if we want to calculate the fitness function value of the solution 0, 1, 1, we can calculate with the Walsh coefficient without any problem, and we check it. That is the same. Okay, so that is no, it's well-defined function. Okay, there are two main properties very important we consider with the Walsh decomposition. The first one is the additive and the scalar multiplication, in which we observe that if a function can be described as a scalar multiplication and a sum of different subfunctions, the Walsh coefficient keep the same relation. It's about the extension of the function domain. For example, if we have a function defined over a domain and we want to extend it, then all the new generated Walsh coefficient to calculate will be 0, whereas the original Walsh coefficient will keep the same value. why these two properties are very helpful? Because we want to, for example, calculate a fitness function, but we know that there is a decomposition of that fitness function. We just study the simpler cases. We calculate the Walsh coefficient, and then we will sum or we multiply according to the relation with the original function to calculate the Walsh coefficient of the higher. For example, in this example, we can observe that to calculate the Walsh coefficient of the function f, we will calculate the Walsh coefficient of the functions f sub 1 and f sub 2, and then we will add it. Okay. Now we will start to calculate the Walsh coefficients of the two presented binary based combinatorial optimization problem, and I will start with the unconstrained binary quadratic problems, in which the solutions are described as binary sequences of length n, and we have a matrix of real values, and the objective is to select the solution that maximizes the values of the matrix M. Without loss of generality, we can consider the matrix M to be upper triangular, and it will simplify the notation of it. We have a brief example. For example, we have the following matrix M, and we calculate all the fitness function values. As I said, there is no problem to consider as an upper triangular. There is an equivalence, and we can redefine it like. So then if we want to calculate, for example, here the solution of the fitness function value of the solution 0, 1, 0, 1, we have to consider the first and the third row, and then taking into account those values, we will calculate the direct. So we calculate the Walsh coefficient, and we observe a pattern that fulfills for any unconstrained binary quadratic problem. Is that we have the overall different values, but for example, all the Walsh coefficients associated to more than 2 variables are always 0. We have checked with other instances, and this always happens. So it's like a pattern that repeats over the problem. So that was our first step, was to prove that that always happens. So as we can see in the following lemma, that's true. We have calculated the exact formulas to calculate the Walsh coefficient, but also we ensure that the Walsh coefficient associated to more than 2 variables will be 0. So that's one way. And then we have the opposite research question, which is given a set of Walsh coefficients, we would like to know if there exists a unconstrained binary quadratic problem instance which generate those rankings of solutions. The following lemma fulfills. In the first part of the lemma, we have the condition to know if they can be described as an unconstrained binary quadratic problem instance, and in the second part of the lemma, we have the exact formula to calculate the coefficient, the real values of the matrix M to generate that Walsh coefficient. So that will be the first problem. In the second problem, we have the number partitioning problem. The objective of the problem is we have a set of numbers and we want to separate them in 2 groups, such that the difference between the 2 groups is the minimal. Overall, if we calculate the number partitioning problem and we study in a direct way, we cannot see any relation with the unconstrained binary quadratic problem. However, there is a transformation and equivalence in which, instead of considering the number partitioning problem directly, if we consider the square that keep the same ordering of the solution, the same rankings of the solution, we can describe any number partitioning problem instance as a particular case of an unconstrained binary quadratic problem instance. So there is a relation with it. So if there is a relation with it, we want to see if that relation is also kept in the Walsh coefficient. The answer is true, and we have, for example, in the following corollary. The first part, as we can observe, the Walsh coefficient associated to more than 2 variables is 0, so that's the same result obtained by the unconstrained binary quadratic problem. But then there are there are new constraints because of the definition of the number partitioning problem. For example, the definition of the exact formula, and also there is a property of symmetry such that it implies that the Walsh coefficient associated to just one variable will be 0. So that's the one direction. We will see the other direction. Given a set of Walsh coefficients, if there is a number partitioning problem instance that generates those Walsh coefficients. The answer is true, and we can also observe that the first 2 conditions are equivalent or very similar to the ones obtained by the unconstrained binary quadratic problem, and after those 2 constraints, we have new constraints that are related with the integer values of the number partitioning problem. So they have the new constraints obtained by the problem. We can also calculate some numbers to generate that set of Walsh coefficients. So we have a summary of the 2 problems. We can observe that the dimensions that they work differently, the problem coefficient that they require to be defined by an instant, and then the number of Walsh coefficients that we cannot ensure to be 0 or not. So that's the first part. So we have observed the Walsh decomposition and the application for 2 binary based combinatorial optimization problems. Okay, so based on those results, we try to extend those results and try to understand why these zeros were appearing. And those results will help us to understand to present a new characterization of pseudo-Boolean function. As we have mentioned, the Walsh coefficient associated to more than two variables is always 0. And if we consider the definition of the Walsh function, we can observe that there is like a partition, there is two groups, which are the solution that always obtain +1 and the solution that obtains -1. If we combine those results, we can observe that there is a condition that must be always fulfilled in the center of the slide. So we have two sets of solutions, which are denoted here with E and O. In the following slide, we will explain why this notation. And then we have that, for example, any unconstrained binary quadratic problem instance must fulfill the following equation, which is related to the fitness function values obtained by the solution with E, the E solutions and the O solutions. So we want to extend this result to a general scenario, which are overall pseudo-Boolean functions. Okay, first of all, the definition and to understand why there is notation. So we will define the solution as even or odd solution according to the number of bits that they have ones or zeros, according to the number of zeros that has the solution. So, for example, if there is a solution with 1 0, it will be odd, whereas in the other case it will be even. Moreover, we can also extend that definition, and instead of considering all the binary variables, we can only consider just a subset of binary variables, and also define even and odd solutions according to the number of zeros. For example, it has been mentioned that for these two groups present a perfectly balanced partition. Perfectly balanced means that there are the same number of even and odd solutions for all the solutions of the search space. We have, for example, a little example in which we can calculate, for example, if a solution is even or odd according to a set of binary variables. No? For example, the solution 111 will always be even, whereas for the other cases they can change even or odd according to the subset of binary variables. So that's the first one. This allows us to present one of the lemmas that will help to present the characterization. The lemma is very long, but the idea is very simple. We have said that the number of even and odd solutions are equally balanced. Okay, we can also check that if there is a few number of binary variables in which we fix the value, that is to say, we ensure that the ith bit must be a 1 or a 0, for example, it will keep as well the same number of even and odd solutions. So that's the main idea of this lemma. It is the notation is a bit complicated, but the idea is simple. With this lemma allows us to present a characterization of pseudo-Boolean function. So we can calculate the degree of a pseudo-Boolean function according if the qualities of even and odd solution is the same or not. For example, that is to say, if we have a pseudo-Boolean function of degree m for any subset of binary variables with more than n elements, it must be kept the equality, whereas there exists at least one in which there is not fulfilled the equality for a set of binary variables of cardinality m. So that's what it says. There is also a corollary in which we can also calculate exactly what is the sum of all the even solutions of all the odd solutions, which is total divided by 2. That's that. Okay, so we have a characterization and we want to take advantage of it and to try to use it in a practical way or something that can be more handleable. So we will to do so. We will present a new definition, which is the word order ranking, in which the word order ranking considers the ranking of the solution, and according to the position of each solution, we will write it as even or odd solution. So we create a sequence of the 2 to the power of n of even and of E and O's. So according to that, that's the word. For example, we can observe that imagine we have the following ranking of solution. So the first solution, for example, is the 111. It's an even solution. The second solution has a 1 0 bit, for example, it's an odd solution, even, odd, and so on. So that's the binary sequences generated from the partition of even and odd solutions. This definition can be extended, and instead of considering all the binary bits of the solution, we can only consider just a subset of solution. Moreover, we can also even present the same idea, but instead of considering all the solution, we want to only consider all the solutions that fulfill a constraint. Let's see with an example. I have considered the same ranking of solution presented in the previous slide. For example, if we define the word according to the subset of binary variables 1 and 3, here the word changes. On the other hand, if we want to if we want to calculate the word defined for only the solution such that the bit 3 must be a 1, we have a reduced word, which is also the following one. So the word of a ranking is a very simplified version to understand how are the even and odd solutions positioned in the ranking of the solution. There is a particular word which is very relevant, and it will be very helpful to understand one of the main results and to take advantage of the characteristics, which are the dig words. Dig words are the words such that any subsequent of the first 3 letters must have always a higher number of even or odd solutions. For example, all the examples presented in the previous slide, if we start counting the number of is and odds, the difference of them, we will see that the first subsequent of e letters will always have a number higher of even solutions than odd solutions. These are there are equivalent problems in the mathematical field to count how many dig words are how many dig words can be generated with this pattern. And some of the problems are the following ones that I show you in the slide. Moreover, the definition of dig words can be also extended to the words defined by a subset of binary variables or the words defined with a constraint. So they can be extended without any problem. Dig words allows us to present one of the most direct results, which says the following one. If we have a ranking of solution whose word is a dig word, then the ranking cannot be generated by the n-1 degree pseudo-Boolean function. So it reduces the space of number of scenarios that the pseudo-Boolean functions can generate. The sketch of the proof is very simple. If we have a dig word, we can match them by pairs, and we can ensure that the quality must be, for example, with the dominant letter is C, we can ensure that the sum of the fitness function, the values of all the even solutions will be higher than the sum of the fitness function values of all the odd solutions. So that's the idea. We can also extend the previous lemma, and we can, instead considering of all the binary variables, we can only consider a subset of binary variables. And it says the following one. If we have a dig word for defined by a binary set, defined by a set of binary variables of cardinality S, then the pseudo-Boolean function must be higher than the cardinality of that set. So that's the first one. So that's one direction. So if we have the dig word, we can understand that they cannot be generated by the pseudo-Boolean. We would like to check the opposite one, which is, imagine we have a ranking of solution whose word is not a dig word. Can we ensure that that ranking can be generated by an n-1 degree pseudo-Boolean function? Well, for the case n equals 3, we have exhaustively verified, and that's true. For greater spaces, we cannot check it. The problem of checking is that the number of scenarios is very large. Remember that, for example, if we are talking about n equals 4, the number of possible permutations is 2 to the power of 4 factorial, which is 16 factorial, which is 20 trillions of rankings. That's the reason why we cannot check it exhaustively. But for the case n equals 3, yes. And if we assume that that conjecture is true, we can exactly calculate the number of rankings that the number of rankings that can only be generated by n degree pseudo-Boolean functions, and it must be n or higher. The cases for the case of a study when the degree of the pseudo-Boolean function is lower than n-1 must be studied. Just to remember, the dig words present a necessary condition to be generated on ranking, but not sufficient. I have an example if you have any doubts, and in which I can show you this one. So, okay, so we have present the characterization of pseudo-Boolean function, and we observe that for pseudo-Boolean functions of degree m, the number of possible scenarios reduced. Now we would like to check those obtained results with the particular binary-based combinatorial optimization problem that we have calculated before. So we will check which are the rankings generated by the unconstrained binary quadratic problem and the number partitioning problem. The inspiration of these experiments is the article titled "We Generating Instances Uniformly at Random," which was presented in this group. And the objectives of our experiment are, first, to quantify the exact number of rankings generated by each problem. Second, we would like to verify that generating artificial instances by sampling coefficients uniformly at random is not the same as sampling instances uniformly at random, which is, it sounds similar, but there is a large difference, and that's the reason why several algorithms might work better than others. And the third one, and the third objective is to try to understand better those rankings generated by the programs. Okay, so we have checked for the two problems. For the unconditional equality problem, we have checked for the case n equals 3. So we need to calculate six real values. The coefficient that we have calculated in the hypercube of dimension 6. It also allows us to calculate the exact space in which each ranking can be generated with an integration. We have also the exact number of the rankings that can be generated in this case, which are the 24,192. And then the sample size, we have started with a 5 million sample, and we'll try to increase 1 million the sample up to generate all the possible rankings of solution. We have obtained that scenario when we reach the 27 million. For the number partitioning problem, we have also considered the similar scenario. We need to calculate first to sample integer values uniformly at random. So we sample n integer values. The space of coefficient we have considered is from 1 to 2 to the power to n plus 2. This is to try to avoid the injectivity, or to avoid the non-injectivity of the rankings. That is to say, there are many scenarios in which if we calculate the exact the number partitioning problem, the value, it will obtain 0 because the function is not injected. So to avoid that, we increase that upper bound. So we are only considering injecting rankings. For the number of possible rankings, we have the exact number for the cases n equals 3 and n equals 4. For the case n equals 5, we have not the exact number, but we are almost sure why it must be this number, and I can explain. And for the sample size, it just with the small sample size. For example, for n equals 3 and 4, with a 1 million sample, it was enough, and for the case n equals 5, it was 5 million. So we have a summary of the obtained result. We can observe, for example, here. I will start with the plot, and then I will go to the table. In the plot, we have ordered the solutions according to the rankings, and we have ordered them in the number of how many times each ranking has been generated uniformly, and they have been ordered from the highest one, which was something like 18,000, things like that, to the bottom one, which are just 1 or 2 times generated. So here we can also observe that there are rankings that are much more times. There are generated more times than the other ones. So to understand, just remember just to reminder, the e-axis is presented in the logarithmical scale. If we don't put the logarithmical scale, the shape is like an L. So just to understand that. The colors of the point represent the number of local optimal solutions considering with the Hamming, sorry, too much names. The Hamming distance, that's it. So the red points indicate that the ranking has only one local optimal solution. The blue points indicate that they have 2 local optimal solutions. The orange one that you cannot see very well, but indicates that they have 3 local optimal solutions. In the table, we're going to see like a brief summary in which we have the exact properties of the rankings and then compare with the sample rankings. That is to say, from the 27 million, how many rankings of solution has 1 local optimal solution, 2 local optimal solution, or 3 local optimal solution. So that's for the case the UBQP. We have repeated the same cases for the number partitioning problem for n equals 3, 4, and 5. The case n equals 3 is not relevant because the final result is that the sampling integral numbers uniformly at random is equivalent to sample instances uniformly at random. For that reason, you could see like a straight line in the plot. So it has no. That's the reason why we are presenting the n equals 4 and the case n equals 5. So here we're going to say like a difference in which, first of all, there are like 3 groups of rankings. The first group, for example, are all the rankings with 3 local optimal solutions. That is to say, all the rankings with 3 local optimal solutions are more times generated than the rest of solutions, and they have also a symmetry among this. That is to say, one ranking can be obtained by other ranking just the permutation of the bits and the direction. So this is relevant because it gives us like a taxonomy or like a classification of the rankings of solution. For the other ones, there is no direct information, but it must be said that, for example, the number of the number of rankings with one local optimal solution has been generated almost 50%. If we repeat the number partitioning problem for the n equal 5, we can also say like a similar shape that we have obtained for the case of the unconstrained quadratic problem. But it must be also mentioned that, for example, the most frequent rankings are the ones with 3 local optimal solutions. Then we start with the 1 local optimal solution, then 2, and finally with 4 local optimal solutions. But the shape and the obtained result is as well similar. So to sum up the presented work, we have 3 parts. In the first part, we have introduced and compute the Walsh decomposition, and we have calculated the Walsh coefficient of several binary-based combinatorial optimization problems. In the second part, we present a characterization of pseudo-Boolean function, and we also study the words and the deep words to try to get advantage of that information. And in the third part, we have run some experiments to try to extract more features about the rankings generated by the unconstrained binary quadratic problem and the number partitioning problem. Which are the future work? First of all, try to extend to new combinatorial optimization problem and constrained combinatorial optimization problem, and to calculate the Walsh coefficient. We also we have in mind to try to find more equivalences among the problems. We need to prove the conjecture, or we must try to prove formally the conjecture of not having a deep word to be generated by an n-1 degree pseudo-Boolean function. Try to extend the generalization of the presented lemmas in the second part of the speech, and finally to try to analyze new combinatorial optimization problems. So that's all. Thank you, and sorry for the
Okay, so thank you very much, Imanol. If anybody has any questions. Okay, maybe I can start with a couple of them. Probably you said it and I missed it, but those 2 problems that you talked about today, you chose them because those were the ones that had that particular characteristic of the Walsh coefficients of 3 variables or more being 0, or you just tried with those 2?
Well, at first, no. The idea was to start with unconstrained binary quadratic problem and then try different other problems. And we started calculating the Walsh coefficients of the number partitioning problem in a direct way. And in that scenario, there is another symmetry and another pattern of the Walsh coefficient. However, when I was reading that literature, I found out that there exists an equivalence of the number partitioning problem and the number partitioning problem with the modification of considering the square of the fitness function. And in that scenario, it is explained that the instance can be generated of the unconstrained binary quadratic problem. So because of that, then we go on with the study, but considering the square of the fitness function, and then we obtain those results. And we observed that equivalence was also shown in the Walsh coefficient.
Yeah, that was another doubt that I had. If you can, probably, yes, but if you can formulate one problem as a specific instance of the other, why do you keep studying both of them? Because
when we study like a smaller one or the constrained one, we can also check how the evolution or the instances, the difficulty of the instances can be solved in order to select the most efficient algorithm to solve it. That is to say, if we have an efficient algorithm that solves the unconstrained binary quadratic problem, that's good. But maybe for the number partitioning problem, there is another algorithm that takes advantage of its definition, and it will be helpful and it will be more efficient to solve it also, even if the equivalent unconstrained binary quadratic instance. That's the reason why we keep on both. Another future work, following your question, is why the number partitioning problem, if we consider directly, has several Walsh coefficient null, But if we take the square, we have obtained more number of zeros in the Walsh coefficient. So we want to check why that transformation is also happening in that case, because it should be logical to understand what is the minimum structure of a problem to have the number of zero Walsh coefficient. Thank you.
Okay.
When speaking about the Walsh decomposition, is it needed to calculate the Walsh coefficients to have pre-calculated all the possible solutions of your search space or of your objective function?
Can you repeat this?
In order to calculate the Walsh coefficient, is it needed to have pre-calculated all the possible functions, values of your search space?
I'm not understanding well, just in...
Yes. The slide of when calculating
the Walsh coefficient of a particular fitness function, it requires to know all the fitness function values.
All the fitness function values?
Yes, but as we, technically yes, but as we have observed here, you need to know all the fitness function values. But as I said, for example, the unconstrained binary quadratic problem, just knowing that it's an unconstrained binary quadratic problem instance, we do not need to calculate all the fitness function values. Why? Because the several solutions can give us the same information as all the solutions. That's the reason which is important. That's the technical part, is just you need to know all of them. But if we understand the definition of the problem, it might not be necessary to calculate all of them. And just calculating a lower number of fitness function values, it will be enough to calculate all the Walsh coefficients.
Well, at the end, the goal is to try to find objection between algorithms and problems. So the first thing is, okay, let's try to make a taxonomy of problems or instances to see, in the second step, we are able to find this kind of objection. You have worked with the unconstrained binary quadratic problem, that is the problem with the lowest structure that is NP-complete. Okay, you have discovered in the case n equal 3 that you have problems with one local optima, 2 local optima, and 3 local optima.
Yes, for the binary quadratic problem, the maximum is 3.
Do you think that the problems with 2 local optima are easier than the problem with 3 local optima? Because apparently, I mean, the intuition says that, but I'm not sure if the intuition is true or not. I would like to know about your intuition about this topic.
That's a good question, because if we are considering the algorithms that work with number of local optimal solutions, the first idea is that the rankings with 2 should be easier than the rankings with 3. But if we are also looking the plot that we have obtained, we can observe that the numbers with 2 local optimal solutions and 3 local optimal solutions are more or less sampled with a small difference. For me, the first intuition is yes. Just the plot, this one. For example, we can observe, for example, the ones with 1 local optimal solution. Yes, I mean, it seems that they are more frequent and they are more less. The ones with 2 local optimal solution, we observe that the sample is, for example, the 20% of the generated rankings of solution. So, in my opinion, I would say yes. because of that, because they are sampled more frequently. The algorithms that are designed for number of local optimal solutions will take advantage that there are not so many avenues or scenarios in which to reach the local optimal solution. I would say yes. However, I will not bet for the one to say that the 3 local optimal solutions must be easier. But yeah.
Just to understand, when you say sampling rankings, you are saying sampling instances, different instances?
We sample parameters of the problem, or in the case of the unconserved quadratic problem, we sample 6 real values which are to define the matrix M, and with the matrix M we calculate the ranking generated by it.
Okay. And then, following the question of José Antonio, when you say it's difficult, you mean difficult for an average of algorithms or for a specific algorithm, or, I mean,
They
you have to define.
They can be algorithms designed to take advantage of the structure of the ranking. In that case, for example, the ones that have lower number of local optimal solutions should be easier than the ones that have higher number of local optimal solutions. But however, there are, for example, cases in which even if there are a lot of rankings that should be considered at first like easier, because they are very extreme case, they are not easy to understand. That is to say, the algorithm designed for the average overall of the problem, and not for the particular cases of that. It would be like a layer of the space of the rankings of solution. So because of that. For example, there is an extension of this experiment that, as I said, I have considered the hypercube of dimension 6. If we have, unfortunately my computer cannot, but if we can calculate the integrate of each ranking, we can calculate exactly the space in which each ranking of solution is generated. And we can calculate the volume, the hypervolume of each ranking of solution. It will be the hypercube divided in the 24,000 hypervolumes, and the total of them should be 1. So the ones that are higher volume, it will be easier to generate. So those algorithms that take advantage of those generated rankings will be optimized, but the ones for the slower or the lowest hypervolume values will be the one that maybe just another algorithm will perform better, because it takes advantage of that.
Could you create a generator of instances taking into account which is the difficulty of, I mean, taking this to my field?
There is, for example, a field in optimization complexity, which is the problem of the phase transition, which is to say in which moment an instance, just with small variations of the parameters, it becomes hard. So there is also a field in the...
So you could use it to create generators for learning algorithms for combinatorial optimization to, just for example, do a curriculum learning where you feed easy instances at the beginning and you keep increasing the difficulty.
Can you repeat the question?
I mean, when you have a neural network, for example, to solve a combinatorial optimization problem, you want to train it with instances, right? And it's a very interesting idea to feed first some easy instances and then go increasing the...
Yes, and you can also, the same idea and the opposite direction. You can take an algorithm that trains with the hard instances to understand why are these instances high or less frequent. And then those algorithms will be optimized better to solve those problems when we generate. And then we have a classification finally we will have a classification that you receive an instance and you say, okay, this is the type 1 or type 2. The easy one, you take algorithm. If it is the 2, okay. It will be a good avenue to follow up with the study, yes.
Okay, thank you.
In the figure, the previous one, I think, when you, yes, are you sure that all the rankings are considered there? Or
yes.
all the possible rankings.
The 24,192 ranking, which fits with the conjecture of the country. That number,
So you know the number of rankings.
This number
for
of
those
rankings is exactly calculated and fits with this formula.
You exactly know the number of rankings
Yes,
of those.
in that case, yes.
Okay.
The only one I don't know with exactly is this one.
Is for 5.
It follows a pattern because, as I said, there is a symmetry between rankings of solutions. So they must be divisible by 5 factorial, which is 120. And this number, and also the number of rankings with 1, 2, 3, and 4 local optimal solutions, all of them are numbers divisible by 120. That's the reason why we believe that.
So your intuition says that all the possible rankings are considered in this figure.
That's the reason.
And have you seen any pattern or something? So if you take all the rankings with just one local optimum, or if you take all the rankings with 2 local optima or that, have you seen any?
The symmetry, the symmetry of the bits. That is to say, for example, in the unconservable quadratic problem, they are defined with 3 bits. If you permute those bits, those rankings are more or less generated the same number of times. So there is for example, there was I think of it, but later, instead of only considering all the rankings of solution, divide all them by the symmetries to classify all of them and calculate the average. In that case, we will observe if the shape is more, like in this case, like in more blocks.
Okay, but I mean, if you well, I don't know if I understood it. I mean, if you have a ranking,
yes.
Is it possible to say that in this ranking we are going to find 3 local optima?
No.
No. So you haven't found any property or something
in advance, no.
That all the rankings with 1 local optimum, maybe they share a property or something.
We were looking for the generated dig words, and there were some patterns on the dig words, but that's not a completely like direct result. But yes, there is some.
But you have found maybe some patterns or some
direct
characteristics
one, no.
or something.
But there is like several characteristics and features that they keep.
One question regarding the coefficients. Is there any relationship between the ranking of the coefficients and the rankings of the solutions?
As I said before, the one here we sample the coefficient to generate rankings, and those rankings are not distributed uniformly and random as the parameters.
Yeah, but if you take the 6 coefficients and you order them as a permutation.
Yeah.
This one is first, this one is second.
You take them. And
is there any relation between these or?
There is a property in which these 3 first coefficients, because are related only with the bit independently, they have more importance or they have more influence in the ranking generated than the other 3 ones, because they require to have more than 1 bit with 1 solution.
But there is no any relation. If you take every possible permutation of 6 coefficients, there is this, let's say, local or general relationship that the first 3 are more important.
Yeah.
But the order in which they are organized,
if they keep the coefficient definition, no, there is no influence.
Let's say for each possible coefficient set of coefficients that you generate, you could sort them and find which is the permutation of the coefficient. Which one is the first, the smallest, the second, the same thing done with the ranking. Is there any relationship between this order and the final ranking?
If I understand it well, I haven't looked at it. Sorry.
I think that the answer is that yes, there is a relation, but one order of the coefficients can generate different rankings of the depending on the
of course
on the values. It can generate different rankings.
Yeah, but I think we haven't gone that way, but that's one of the most important way. I mean, the idea of having a relation between the Fourier coefficient and the rankings, that's the most relevant relation, and this is really difficult. I haven't thought about the idea of considering a permutation of the values of the. I mean, one way, and probably one easy way, is the easiest way is the one that you said, that is going through the permutation of the Fourier coefficients and see what is going on, because imagine that given yeah, I mean, you can do with the coefficient of the instances, but you can also do with the coefficients of the Fourier coefficients.
Yeah.
From my point of view, it's more interesting from the point of view of the Fourier coefficients, because you have a lower number of coefficients. And try to imagine that you discover that when there is this ranking of coefficients, when there is the ranking of coefficient in the Fourier transform, if you can only generate problems with one local optima, that would be unbelievable. But I don't think that the answer is going to be so easy.
Okay, thank you. So, any more questions? Okay, thank you very much, Imanol, for the talk.